Hello guys, welcome on Tesla Adventures. In this video, we are starting the pendulum, and there are three kinds of pendulums. The first one is the simple pendulum, the other one is the physical or compound pendulum, and the third one is the toroidal pendulum. Let us start our discussion with the simple pendulum. So this is a simple pendulum, as you can see, and in this simple pendulum there is a ball of mass m, and it is attached with a rope of length L. The rope is fixed to the ceiling at this point, and this ball is made to oscillate about the mean position like that. So we have to find out the time period of oscillation for small angles or for a small angular amplitude. So we are considering that theta is small. Okay, so let us first of all write down the torque of mg, which will act in this position, and it will bring back this pendulum into its original position like that, in the mean position. So this force which is acting in the downward direction is mg, and the torque of this force is, let's suppose the length of this rope is L. So this distance will be L sine theta. So the torque of this force will be mg into L sine theta. And for small angles, sine theta is approximately equal to theta. So the torque will be equal to mgl theta. Now this torque is equated to I alpha, and this torque is mgl theta, where I is the moment of inertia of this mass about the hinge point, and therefore this moment of inertia will be ml square, and alpha will be omega square theta. Cancelling this theta with theta, m with m and L with L. So omega square will be equal to g by L, and omega will be equal to under root of g by L. So omega will be 2 pi by t, and that would be under root of g by L. So t would be equal to 2 pi under root of L by g. So this is the time period of simple pendulum, and this is only valid when this angular displacement or angular amplitude is very small. Now let's move on the next part. Now we are going to discuss that the simple pendulum is being applied with some external constant force. Then what will be the effect on the time period of the simple pendulum? So if this pendulum, there is a pendulum ball which has a mass of m, and there is some charge q placed on this ball. Now the length of this rope is L, and some electric field E is applied on this ball in the downward direction. We have to find out the time period of its small SHM. So you can follow the exactly same procedure which we have followed in this case, in which we have calculated the torque of this force. But in this case, when we'll take the displaced position, then the torque will be of mg as well as of qe. So we can follow the exactly same procedure to find out the time period. But we are discussing the short trick to calculate the time period of this pendulum, which is in the effect of some external force. So first of all, let us we have to find out the I am writing down the steps. So the first step 1 is to find out the mean position, and to calculate the tension in the mean position. So this is the mean position. You can see that pendulum would be in rest in this position, and we have to calculate the tension in this rope in the mean position. So first of all, let us suppose that T is acting on this ball in the upward direction, and mg is acting in the downward direction, as well as QE is acting in the downward direction. So the tension in the mean position will be QE plus mg. Now this is the step 1. I am repeating the step 1 again, that we have to find out the mean position of this pendulum with the new force acting on it, and we have to find out the tension acting in the rope in this mean position. Now the step 2 says that we have to find out G effective. So G effective would be equal to T by M, where T was the tension in the mean position. So we have already calculated this tension, which is QE plus mg, and therefore G effective would be QE plus mg divided by M. So G effective would be QE by M plus G. So this is the effective acceleration due to gravity. Now we can write down the time period of simple pendulum as 2 pi under root L by G effective. So this is T is equal to 2 pi under root L by G effective is Q E by M plus G. So this is the time period of this simple pendulum when some external force is acting on it. Now let us take the different case. Now in this case, you can see that this pendulum is situated inside a lift which is accelerating in the upward direction. So we have to find out the time period of small SHM of this pendulum, in this case inside the lift. So again, let us find out the time period by using those steps which I have told in this case. So the step 1 says that we have to find out the mean position. So you can see that for an observer which is standing inside this lift, this would be the mean position, and the tension is acting in the upward direction, which is balancing mg plus pseudo force, which is ma. Now this tension will be equal to mg plus ma, and now when we have to find out the G effective, then G effective will be equal to T by M. So T by M is G plus A. Therefore the time period of simple pendulum would be 2 pi under root L by G effective. So this is 2 pi under root L by G plus A. So this is the time period, required time period of the simple pendulum in this case. Now if this cart is moving in the forward direction like that, so we know that in this case the pendulum would not be vertical in the mean position, and therefore it would be like that, because a pseudo force of ma would be acting in the backward direction, mg would be acting in the downward direction. If this angle is theta, then this angle would also be theta, and this tension T will be equal to under root of G square plus A square. So T will be equal to M under root of G square plus A square, and G effective will be equal to T by M. So this is under root of G square plus A square. So the time period of this simple pendulum would be 2 pi under root of L by G effective, which is under root of G square plus A square. So this is the time period in this case. Now let us discuss some of the questions which are based on simple pendulums. Now let us discuss some of the numerical problems which are based on simple pendulum. So in this question, there is a simple pendulum whose suspension point is moving with an acceleration of alpha 1 I cap minus alpha 2 j cap with respect to Earth. So let us draw this suspension point, and this is moving with alpha 1 I cap and alpha 2 j cap. So its acceleration would be like that. So this is alpha is equal to alpha 1 I cap plus alpha 2 j cap, in fact minus alpha 2 j cap. So this pendulum has a suspension point which is accelerating in the fourth quadrant. Now you can find out the mean position. First of all, we have to check the pseudo forces which are acting on this pendulum. Now we know that there would be two components of this acceleration. This component in the x direction would be alpha 1 and this would be the alpha 2. So a pseudo force would be acting upon this pendulum ball in the backward direction like that. So let us draw this pseudo force like that. This is m alpha 1 and mg would be acting in the downward direction, while another pseudo force m alpha 2 would be acting in the upward direction. So we are considering the fact that mg is greater than m alpha 2, because then only it would oscillate, and therefore the net force acting in the downward direction, or we can say the net force, will be acting like that, and this would be the tension. So the net force will be equal to the resultant of these three forces. So it would be under root of mg minus m alpha 2 whole square, mg minus m alpha 2 whole square plus m alpha 1 whole square. So this net force will be equal to tension, and therefore G effective will be equal to T by M. So T by M will be equal to under root of G minus alpha 2 whole square plus alpha 1 whole square. So the time period of SHM would be T is equal to 2 pi under root of L by G effective. So the correct option would be option number A. Now let's move on the next question. Now in this question, there are two pendulums of different length. They start swinging together from rest, and their length are equal to 1.44 meter and 1 meter. So we have to find out that after what time and after what number of vibrations they will start to swing in the same phase, or we can say that after beginning of the oscillation, in how much time they will be in the same phase again. So first of all, let us find out the time period ratio of those pendulums. So if the first pendulum T1 has a time period of 2 pi under root 1.44 upon G, then the second pendulum is having the time period of 2 pi under root 1 by G. So you can say that T1 by T2 is equal to 1.2 and T1 is equal to 5, in fact 6 by 5 of T2. So if I can say that if T1 by T2 has a ratio of 6 by 5, then it means that if T1 is 6, then T2 will be 5. So this is the longer pendulum. This one is longer. It has a greater length of rope. So in these kind of questions, we have to find out that common time in which they will complete their integral number of oscillations. For example, if a pendulum is having a time period of 1 second and the other pendulum is having a time period of 2 seconds, then that common time in which they will complete any integral number of oscillations would be 2 seconds. We are finding out that common minimum time, because in 2 seconds this pendulum would complete one oscillation, and in 2 seconds this pendulum would complete 2 oscillations. So they will be again swinging in the same phase. So in these kind of questions we have to find out the LCM. So if we check T1 and T2, then the LCM of T1 and T2 is 30. So in 30 seconds they would be swinging in the same phase, and therefore in 30 seconds the number of oscillations of the longer pendulum, which has a time period of 6 seconds, would be 5, because in 30 seconds this pendulum would complete 5 oscillations, and in 30 seconds the shorter pendulum would complete 6 oscillations. So we have to find out the number of oscillations completed by the longer pendulum, and that would be 5 vibrations. So the correct answer would be option number D. Now let's move on the next question. In this question, there is a simple pendulum of length L and whose mass is n. It is executing small SHM of amplitude A, and we have to find out the maximum tension in the string of the pendulum. So let us draw the displaced position and the mean position. So this is the mean position and this is the displaced position. The amplitude is linear amplitude, and therefore it would be A, and therefore the velocity of this ball when it will pass through the mean position will be the maximum velocity, and this maximum velocity will be A omega, where omega will be equal to under root of G by L, which is the angular frequency of SHM. So the tension T will be maximum in the lower most position of this ball, and this maximum tension will be equal to mg mg plus mv square by L plus mv square by L, and this is mg plus m by L, and v square will be a square omega square. So we know that this is a square and omega square is G by L. So taking this mg common, and this is 1 plus a square by L square. So the correct option will be option number C. Now let's move on the next question. In this question, you can see that there is a pendulum ball which is connected with a rope of length L, and the pivot point is P. It has an amplitude of beta, and if this ball, when this ball passes through the mean position and goes on the other way of the mean position, other side of the mean position, then it encounters a wall on which it encounters a perfectly elastic collision, and it bounces back and then comes again to the original amplitude beta on the other side of the mean position. So all in all, it oscillates like that this is the angular amplitude, and it goes like that, and then it collides elastically with this wall and rebounces, and then again goes to this mean position. So we have to find out the time period of this pendulum. So first of all, we know that let us find out the half time T by 2 of the oscillation. So let us find out this time T1 and this time T2. Now this till the time when this pendulum reaches the mean position from the extreme position. So this time T1 will be the time period of free oscillation of the pendulum, and in fact this will be the 1/4 time of the time period of free oscillation. So we know that for free oscillation the time period is 2 pi under root L by G. So this time T1 will be equal to pi by 2 under root L by G. Now we have to find out this time T2. So let us write down the equation of this simple pendulum, the equation of SHM of this simple pendulum in angular form. In linear form, we know that x is equal to a sine omega t. Okay, and in angular form, x will be replaced by angular displacement, which is theta. This is the maximum angular displacement, which is beta in this case, and this is sine omega t. So we are finding out the time taken by the pendulum to reach from mean position to this angular displacement alpha. So alpha will be equal to beta sine omega t, and sine omega t will be equal to alpha upon beta. So omega t will be equal to sine inverse alpha upon beta, and omega is under root g by L. So t will be equal to under root of L by g sine inverse alpha by beta. This is time t2. Now the total time period will be twice of t1 plus t2, because t1 plus t2 is only the time which is half of the complete oscillation. So this is t1 plus t2, and the time to return back will be t1 plus t2. So the total time period will be twice of t1 plus t2. So this is twice of pi by 2 under root L by g plus under root L by g sine inverse alpha by beta. So you can see that the correct option will be option number B. Now you all know that pi by 2 plus sine inverse beta by alpha can also be written as cos inverse minus beta by alpha. So the correct option is also the option number D. Now let's move on the next question. In this figure, you can see that this is a graph of kinetic energy versus the angular displacement of a simple pendulum. This is given in milliradians and this is in millijoules. The mass of the pendulum ball is 0.2 kg, and we have to find out the length of the pendulum ball. Now first of all, the angular displacement or angular amplitude is given as 100 milliradians, which is 10 raised to power minus 3 radians. So this is 1 by 10 radians, and therefore the amplitude, linear amplitude, will be L into theta. So A will be equal to L by 10, and the maximum velocity will be equal to A omega, and A is L by 10 and omega is under root of G by L. We all know that. Now the kinetic energy maximum is given as 15 millijoules, which is 15 into 10 raised to power minus 3, and this is half m into V max square. So 15 into 10 raised to power minus 3 is equal to 1 by 2. M is 0.2, which is 1 by 5. And this V max square will be L square by 100 into G, which is given as 10, and divided by L. So you can see that this is 10 and this is 10, and 10 into 10 is 100. So this is 1.5 is equal to L square, in fact L, and this L, this 1.5 can be written as 15 by 10. So L will be equal to 15 by 10, and if we compare it with this one, then N will be equal to 15. So the correct answer is 15. Now let's move on the next question.